At Lone Star, we help make predictions. So how does anyone make a prediction? Whether that's in your head, whether it's an Excel spreadsheet, whether you're using the latest machine learning algorithms, to make a prediction, you have to determine the influencing factors. And you have to determine what influences those influencing factors. So the first challenge is knowing where to stop. But even if you have found some way to avoid boiling the ocean, you then need to put numbers against those influencing factors. You need to apply data. And most organizations struggle with getting that data. They have messy data or dirty data or missing data, or they simply can't get to the data. It's too dispersed or is held onto by suppliers. And even when they've managed to overcome that struggle of getting the data, they normally only put single values, single numbers against each influencing factors. And the problem with single numbers is, no matter how smart the maths are, when you use single numbers, especially averages upon averages upon averages, those single numbers will result in a wrong prediction. And not just specifically wrong, but generally wrong. And so what we do at Lone Star is recognize that the future, which is what predictions are concerned about, isn't one fixed point. It's a range of possibilities. It has a lot of uncertainty. But so does the present. If I were to ask, how deep is the Nile? It depends on who I'm asking. It depends on where they're standing. It depends on the time of day and the time of year. So for each influencing factor, we ask, what would it be typically? And what 1 in 10 times might it be as low as? And what 1 in 10 times might it be as high as? And we bound it. What will it never be lower than? What will it never be higher than? And what you also notice here is the high of 195 in this example is much further away from the typical number of 50 and the low of 30. It's asymmetric. And most things in life, in reality, are just like that. So what we do is we create those ranges of uncertainty by looking at the data sources and from speaking to people that have previous or similar experience. We apply that approach for every single influencing factor. And why is that important? Well, 340 and 1.2 is a very different combination, a very different view of the world from 25 and 50. So what do we do once we've got those ranges? We run hundreds of thousands of simulations, randomly selecting from every single possible value in that range of uncertainty that each influencing factor. And we then run hundreds of thousands of simulations on every single combination of each influencing factor for each range, running all the way to the end prediction. And what that does is it gives us a prediction that's more accurate, that's more likely to reflect future reality. But it also gives us a prediction with a range as well. This shows there's a 50% chance it could be 16 or higher or lower. It's also telling us there's a 30% chance it could be 4 or lower, and a 70% chance it could be 28 or lower. But it doesn't just stop there. Because of the way we've built those ranges of uncertainty and the way we've simulated all those possible worlds, those combinations of uncertainty, we can also understand what's the most important influencing factor in making that prediction. So, if we think of the whole thing like a series of dials, and here we're going to use the simple example of predicting the completion date of an asset undergoing an overhaul period, we could look up to the left and see the days required for receiving and induction. This process has a fair amount of variability, of uncertainty, and influences both maintenance time required and supply time required to complete the work, both affecting final delivery date. But by running those simulations, we can tell that even though there is uncertainty, the induction process doesn't have a large impact on asset completion date. Whereas if we look down here, while scheduled repairs have a lot less uncertainty, but not none, it's still skewed to the right, there is a lot of sensitivity from that maintenance having a much greater impact on the asset delivery schedule as compared to the induction process. Now, if we look at unscheduled repairs, there's both a very large amount of uncertainty, typically it's going to take 12 days or so, could be 1 day, could be 40 days, but it also has a big impact on the asset completion date. And recognizing that helps us to prioritize what part of the organization, of the system, of the structure, of the resources that we really need to focus our efforts and attention on. Now, this alone is an incredibly powerful advantage to be able to make predictions this way. But leaders also want to be able to ask the question, what if? What if we change something? What if we were able to intervene and change the range of days for unscheduled repairs? What would that do to the asset completion prediction? We can rerun those hundreds of thousands of simulations with the new input that allows us to create scenarios, courses of action, predictions about a possibly different future. On this example, there's now a 50% chance that the asset completion date could be on the 9th. There's a 30% chance it could finish as early as the 4th or earlier, and there's a 70% chance it will finish on the 10th or earlier. But we can go even further. While most leaders want to make predictions and run courses of action scenarios, they also want to set a goal. They want to say, my goal is for it to be completed on the 7th. I'd like to fix scheduled maintenance time to no more than 30 days. Now tell me, what would the influencing factors need to be? Much of what we discussed so far is called stochastic modeling, and this goal-setting approach is called adaptive non-convex stochastic optimization for machine learning. For this, Lone Star deploys evolved AI, which allows us to work backwards to determine the ranges for each influencing factor that needs to be hit to achieve your goals. And then, as we run through that change, as you hit your targets, as you change the organization to work with that uncertainty, you achieve your objective. So what does it all look like to a decision maker? What do they see on their screen? Well, to explain and describe the predictions, we focus on simple charts. So what you can see here is that there's a likely 50% chance of it being 6. There's a 30% chance of it being just over 5 or lower, and there's a 70% chance of it being 6.74 or lower. We call that the likely range. There's also a 10% chance it'll be 4.3 or lower, and a 90% chance it'll be 7.7 or lower. That's the possible range. Now, that's for a prediction that's a point in time. We also want to know about changes over time. We want to forecast into the future. So if we take the whole concept of the likely and the possible and we imagine turning it on its side, we can then run through forecasts into the future. So what you're seeing here is the same idea, the likely and the possible, but you're also seeing layers change over time. Now those layers, they could be days, weeks, minutes, years, milliseconds, or decades. Now that's the prediction. To explain the impact, we use a different chart. Leaders and decision makers often have big discussions and even arguments about what the biggest drivers of a situation or a prediction are, and therefore what to tackle and change. Using this diagram, for each influencing factor, we can describe its impact on the final prediction and its uncertainty. X is the biggest influencing factor, and if it isn't something you can change or mitigate or don't want to change, then focus on B. Now, what we also do is build models that are in themselves inherently understandable. They're not locked in code or in opaque black boxes of AI. This is what a real model looks like. This is 9 or 10 elements out of a larger model that is tens of thousands of influencing factors large when you zoom out. For each one of the influencing factors, where the grays are inputs and the greens are calculations, this is where we put the data, taken from any data source and combined with the views of people with that previous or similar experience. We apply those ranges to all the inputs, and right there in front of the decision maker, it generates the predictions. It's often very difficult for leaders to work with other leaders to make shared decisions. It means that decisions often default to the hippo, to the highest paid person's opinion. Or other leaders might have a different agenda because they're working on the latest fire. You've got other leaders still pushing their view who have zero evidence but are really arrogant. And you've got other people who don't yet see that they have skin in the game. They're really here in name only. But by having a shared view, dealing with the data that you have, not you wish you had, by embracing uncertainty, you can make predictions, create scenarios, set goals, and collectively make changes that you can all sign up to. And so, ultimately, Lone Star's approach is about helping you make predictions, helping you run scenarios, and helping you achieve your goals.